All right, so we're going to do lesson 2.2 this week. Something's wrong, I know. 2.2a. There's not really any letters today. It's just examples. All right, we're doing limits involving infinity. Limits involving infinity. We're also going to talk about horizontal asymptotes, because whenever you go out to infinity for x, you end up with a horizontal asymptote sometimes. Okay, so here we go. We're going to start with a theorem. And it says here, the line y equals b is a horizontal asymptote if, and I tried explaining this to my ham kids, but it's really hard because they've never done limits before. And the definition that the book gives them is for limits. But you get y equals b as a horizontal asymptote if the limit as x goes to plus or minus infinity of a function f of x is equal to b. Okay, so as x moves as far to the right as you can get it, and your y value is approaching a constant b, then that is a horizontal asymptote, just so happens to be. So let's take a look real quickly at something like y equals let's do 2x plus 3 over my thing just fell out. That's so funny. Sorry. This I don't know what's going on. I don't know. I thought I had two, but oh, here's my other one. I'll try this one. They're not working out very well. X minus 1. Okay? So I have one, but it clicks. This? That? It clicks though. Yeah, when you hear it on the video. I'll show you. I'll do it, okay? All right, so go ahead and graph this. Graph this on your calculator. So get your calculator out, and we'll graph y1, 2x plus 3, divided by x minus 1. Ooh, lots of, yeah. You're going to need lots of parentheses when you graph this. So parentheses 2x plus 3 divided by x minus 1. Hit zoom 6. And you get one of those rational functions that you graphed in ham. Okay, I'm just going to draw a sketch of it. Ooh, you know what? Okay. There we go. All right, so we're looking for the horizontal asymptote, and you can do that by using limits. So you could take the limit as x approaches infinity. So even go to your graph, hit trace. I want to go up to there. Okay, and then go out towards infinity. Keep going for a long time, as long as you want to. And you'll see, and you can even go to the table. People like to go to the table, and they like to follow x out to infinity, and there's 2.3, 2.2, 2.1. You can go really far, but this is going to approach the limit as x goes to infinity is equal to 2, which means that at y equals 2, there is a horizontal asymptote right through there, horizontal asymptote. If they're looking for the asymptote, yes, you do. If they're just asking you what the limit is and you say 2, that's different. That's fine too. Okay, now we learned back in Honors Advanced Math or Regular Advanced Math that there were 3 cases for these. Do Remember the one where the coefficients were, when they were equal, that was what your horizontal asymptote was? I don't know if you remember that.
The degrees?
Yeah. So, yeah, if you talk about the 3 cases for horizontal asymptotes, that can help you find the limits at infinity. So let's do those real quick. So there are 3 cases here. And this is only for these types of functions, these rational functions. So it's for f of x equals n of x over d of x, where n of x and d of x are both polynomials. Okay? So you have a polynomial over a polynomial. And here are your 3 cases. Case number 1. Now we're talking about the degrees, okay? So if the degree of n of x is greater than the degree of d of x. If n of x is bigger than d of x, okay? So something like y equals 3x cubed plus x over x plus 1. Something like that. Now, as x is going out to infinity, what's happening is the top is becoming bigger than the bottom, a lot bigger, right? If I cube infinity and then add infinity, but I divide by just 1 infinity plus 1, then this is going off to infinity. So y would go to infinity also. So then there would be no horizontal asymptote. No horizontal asymptote. Okay, it's going off to infinity. It's getting bigger and bigger and bigger. All right, case number 2. If the degree of n of x is less than the degree of d of x. Okay, so something like this. Y equals x minus 4 over x squared plus 3. Something like that. So there's a polynomial over a polynomial. It's a rational function. And what we get is we get the numerator of the numerator degree is 1. The denominator degree is 2. So as x is going to infinity, I'm getting a huge number on the bottom. Because I'm squaring that number. It's getting even bigger than the top. And so what happens is y is going to 0. Okay? Think about 1 over 100, and then 1 over 1,000, and then 1 over 1,000,000. Right? The bottom's getting increasingly bigger than the top, and so this is going to 0. It's getting closer and closer to 0. Okay, and then finally the third one. Yes, the asymptote would be y equals 0. Thank you. Y equals 0 would be the asymptote. So no asymptote for the first one, y equals 0 for the second one. And then for 3, if their degrees are equal. So the degree of the numerator equals the degree of the denominator. And we did one just a minute ago. So something like y equals 5x plus 4 over 2x minus 1. Okay? Basically, you think, oh, if I plug in infinity, I'm going to have infinity over infinity. So they're going to kind of cancel or, reduce each other out. And what I end up with is 5 over 2. So then y would equal, for the asymptote, the leading coefficient. Sorry, that looks really gross. The leading coefficient over the leading coefficient. The leading coefficient of the numerator over the leading coefficient of the denominator. And that's what we got in that last one. Do you see that? It was 2x over 1x, and that's what it is. Okay, so let's do some now. You can use this to either find the asymptote if they're asking for that, or you can use it to find the limit. So let's do number 1. we're going to find the limit as x goes to infinity for 2x squared plus x minus 1 over x cubed minus 4x. Okay. You don't need to worry about reducing things or, oh, do things cancel out or whatever. You don't need to worry about any of that. Okay. I like to kind of plug infinity in a way, and really you kind of look at just this and that. The rest of it doesn't matter that much. So what happens is I have an x squared over an x cubed, which reduces to 2 over x. And if I plug infinity into that, I get 2 over infinity. Well, what's that approaching? 0. The numerator has a smaller degree than the denominator. The denominator kind of wins. Okay. Sometimes they'll give you a little twist. Number 2. They'll tell you, let's find the limit as x goes to infinity for 3 plus 2x plus 1 over x minus 4. Something like that. Okay? They put that 3 out there. Now, what you want to do is you want to take the properties that we learned last week, and you want to split this up into 2 limits. So we're going to take the limit as x goes to infinity for 3 plus the limit as x goes to infinity for 2x plus 1 over x minus 4. So you split it up into 2 limits. Now let's talk about the limit as x goes to infinity for 3. What's the, yeah, exactly. What's the graph of 3? Y equals 3 is just a horizontal line. As I'm going out towards infinity or negative infinity, it doesn't matter. My limit there is always 3. Y is always approaching 3. It actually equals 3, but it's approaching it. And then plus, yes, this one right here, we're going to use our leading coefficients, because what happens is you get 2x over x. The x is kind of reduced. That's the way you can kind of think about that. The limit as x approaches infinity for 2 is just 2, and so my answer would be 5. We did these in ham, by the way. I don't know if you remember.
So we don't care about anything after the leading coefficient?
No, you really don't. Yeah. Kind of like ignore everything and just use those. Yeah. It has to do with end behavior. End behavior model is always like the first part when it's in descending order. Yeah. Okay. Now, what if it's not a rational function? So let's do some of those. You will be able to use your calculator. Okay. So let's do number 3. Let's find out the limit as x goes to infinity for the sine of x over x. Now we've seen the sine of x over x, and we actually took the limit as x goes to 0 for this, and we got 1. Do you remember what the graph looks like for this one? You can graph it, but what it does is it oscillates back and forth here, and it goes up to here, and then it goes like this. So we've taken the limit as x approaches 0, and we get 1. But now we're not doing that. We're taking the limit as x approaches infinity. So as we go out towards infinity, and you can graph this if you want to on your calculator. Take a look. You can follow the table out. You can follow the graph out. You can hit trace. Anything you want to do to help you with this. But what it does is it's getting closer and closer to 0 on either side of it. It just keeps going back and forth. And so then the limit would be 0. And that you would need to do, we don't do that one algebraically, we do it graphically. Okay, it does have a horizontal asymptote. And I know a lot of people think that a horizontal asymptote means that your graph doesn't touch it. That's not true. Graphs can touch horizontal asymptotes. As you take, when you graph it, as you take it, you hit trace, and you go out towards infinity, it just keeps getting closer and closer to 0 on either side of 0 as you go along. All right, another one that you will get, ooh, let's do this one, number 4. This is a two-parter. Why isn't that working? I don't know. I know, I think it's the iPad. I don't think it's the stylus. I think it's the iPad. I need to go talk to Mr. Parsons. I know, let's put in a request for that. All right, let's take the limit, or let's say that f of x is equal to x over the square root of x squared plus 1. So this is not a rational function, okay? The top is a polynomial, but the bottom is not because it's a radical. We're going to do two things. Letter A. I shouldn't have written A right there. Sorry. Letter A. Let's find the limit as x approaches infinity for f of x. And then let's find the limit as x approaches negative infinity for f of x. Okay, so go ahead and graph this one. Go to your calculators, graph it. It's an interesting graph. I don't think you've ever graphed something like this before. Maybe you have. X divided by the square root of x squared plus 1. All right, so I just hit zoom 6. Oh, that's not as exciting as I thought it was going to be. Kind of boring. But what it does is it goes like this, and it goes like that. Okay. Now, this one actually has two horizontal asymptotes. It has the horizontal asymptote that's affecting the right side of the graph as you go out to infinity, and it has a horizontal asymptote affecting the left side of the graph as you go out to negative infinity. Does anyone know what that is? Can you hit graph or trace? Did you trace it out? Yes, it is 1. So as you hit trace and you keep going out towards infinity, your graph is not going to get any higher than 1. So that's going to be 1. Yes, and the other one, as you go out towards negative infinity, that direction, your y values are not going to go past negative 1. No, not always. In this kind of problem they will be, but not all the time. They don't have to be. Okay, let me see if I've skipped anything. Let's do this one, number 5. Let's do, find the limit as x approaches infinity for e to the negative x. And let's find the limit as x approaches negative infinity. See, why did it just erase? It's like glitching. Look at it, won't even write. E to the negative x, okay? And then we want to find out if there are any horizontal asymptotes. Okay, that's not how you spell horizontal. By the way, horizontal asymptotes come from either here, where x is approaching infinity, or x is approaching negative infinity. If I get an answer for either one of those, that will be a horizontal asymptote. So that last problem, I actually have 2 horizontal asymptotes. There's a horizontal asymptote at 1, and there's also a horizontal asymptote at negative 1. Okay? So it could occur at either spot, here or here. That'll give us our horizontal asymptotes. All right, so let's graph this one. Go to your calculator, and we do e to the negative x. You should maybe kind of have an idea of what that looks like. It's an exponential function, but it's a negative x, so it's going to be decreasing like this. Okay, so let's talk about the limit. Now, the limit as x goes out to infinity, there is a horizontal asymptote here at y equals 0. So as I go out towards infinity, I get 0 for my limit. As I go towards x is negative infinity, I'm doing e to the negative infinity, which is e to the infinity. Guess what that's going towards? Infinity. And so I get one horizontal asymptote here, and my horizontal asymptote would be at y equals 0. All right, I think I did it all.